So far this semester, the vast majority of the proofs that we've seen have been some variation on the theme of direct proof. Our first proof template of the semester was for a direct proof of an if-then theorem. The approach embodied by that first template for proving that P implies Q is to hypothesize that P is true and show that then Q must also be true. So whenever we are in the top half of the truth table, we are specifically in the top row. And many of the other proof templates that we've seen so far have been applying this same core idea of direct proof to different settings. But hypothesizing P to be true and showing that this gives us Q is not the only way to prove a statement like P implies Q. And our topic for today is two other ways of proving this sort of implication that correspond to two other columns of this truth table. When we write out the truth table for not Q implies not P, we see that it is identical for the truth table for P implies Q. This is known as the contrapositive of the original implication, and it gives us another approach for proving the statement P implies Q. In particular, if we want to prove the statement P implies Q, we could apply the direct proof template to the contrapositive of the statement. That would mean assuming not Q and showing that in such a case, not P follows. We can use this idea of proof by contrapositive as an alternative to many of the variations on direct proof that we have seen in other proof templates. For example, if we want to prove a subset relationship, then that boils down to an if-then statement about elements of the sets, and we could prove that if-then statement using its contrapositive. Similarly, if we want to prove an if and only if statement, that breaks down into two if-then statements for the two directions, and we could prove either or both of those using the contrapositive. So let's take a look at a basic example of proof by contrapositive. When we use our proof by contrapositive template, it helps to say so at the beginning so the reader knows why we are hypothesizing not B. The contrapositive of P implies Q is not Q implies not P, so we get the negation of the right-hand side implies the negation of the left-hand side. But let's think about what these negations mean. If we're saying that it's not true for A plus B to be greater than or equal to 15, we are saying that A plus B must be less than 15. And on the left, we can apply De Morgan's law to turn the negation of an or into the and of negations. So we would have not A greater than or equal to 8 and not B greater than or equal to 8. And to say that A is not greater than or equal to 8 is the same as saying that A is less than 8. So now that we have taken the contrapositive of our original statement, we can make a direct proof of this if-then statement. We can assume that A and B are less than 8 and show that therefore A plus B must be less than 15. If A and B are integers that are strictly less than 8, we know they must be less than or equal to 7. And now we can add these two equations together. And finally, we can conclude that A plus B If it's less than or equal to 14, it is clearly strictly less than 15. And so now, having shown the conclusion of our contrapositive implication, we've shown that if the negation of B, then the negation of A, and so we've shown that A implies B. We have one more column of our truth table that is equivalent to P implies Q, that is, P and not Q implies false. And this column serves as the basis for our proof by contradiction template. The idea of proof by contradiction is that we can do a direct proof of this if-then statement. That means that we are hypothesizing P and not Q and trying to reach the conclusion false. So that means that we are trying to, by a sequence of steps, arrive at a conclusion that is false, meaning we are trying to arrive at a contradictory statement. In a proof by contradiction, we are trying to show that P implies Q, and we do that by hypothesizing that P and not Q are both true, and then by a series of steps arriving at any contradictory statement. And so if P and not Q, both being simultaneously true, implies something false, then that means that P implies Q because we have the same truth table. Another way to think about this is that we are pretending that we are in the case where P is true and not Q is true, and that is exactly the case that makes P implies Q false. And if we can show that it is absurd because a contradiction would arise that P is true and Q is false, then we have shown that it is impossible to be in the case where P implies Q is false. So we hypothesize A and not B, but again, it helps to identify to the reader that we are using a proof by contradiction. So we are supposing not B goes along with A, and we are trying to arrive at a contradiction, which must mean that, in fact, B was true whenever A was true. And it is traditional at the end of a proof by contradiction to have some symbol indicating that you have reached a contradiction, and therefore the thing that you supposed must not hold. And there are lots of symbols for this. You might see implication arrows pointing towards each other, or you might see a lightning bolt, but my personal favorite is crossed swords, indicating the contradiction. Let's do an example of a proof by contradiction, and we're going to need a little bit more space, so I will erase our contrapositive template. But before I do, it's worth reinforcing that even though we are teaching them together, and contradiction and contrapositive sound similar, and they can both be used to prove implication statements, they are fundamentally different proof templates. In a contrapositive proof, we are still doing a direct proof of an if-then statement. We've just switched which way the arrow points and negated both statements. On the other hand, a proof by contradiction has a very different feeling because the thing we are trying to get to at the end is not actually the conclusion of our proof, but rather some contradiction that allows us to conclude that the thing we assumed must be wrong. So proof by contrapositive will feel much more like the proof templates that we have been using so far. It's just another variation that gives us more options, whereas proof by contradiction has a very different feel to the way the proof operates, and will take some practice to get used to if you haven't done proof by contradiction before. Here we have an if-then theorem that we want to prove by contradiction. So we are trying to show that if a squared is even, then a is even. We'll begin by assuming that a squared is even. So we've hypothesized the left-hand side of our implication, and now we want to hypothesize toward contradiction the negation of the right-hand side. We want to assume the negation of a is even, which is equivalent to saying a is odd. And now our goal is to use the fact that a squared is even, but a is odd, to arrive at some contradiction. Because a is odd, there's some integer x, where 2x plus 1 gives us a. We can square both sides, and then we can simplify and factor out a 2. And now we've shown that a squared is odd, which contradicts our original hypothesis. Since we arrived at a contradiction, we can conclude that one of our assumptions must have been false, and so that means that if a squared was even, our other assumption must have been false, that a was odd, and so we can conclude that if a squared is even, then a is also even, which gives us a proof of the theorem that we claimed. But it's worth noting that this didn't need to be a proof by contradiction. We definitely could have proven this statement in other ways, for example with a direct proof. And at the end of the assigned reading for today, the book suggests a couple of checks that you can look for in your proofs by contradiction to see if they can be simplified. I suggest comparing this proof to those checks, and you should find that the book recommends how we could translate this proof by contradiction into instead a proof by contrapositive that would be clearer because we don't actually need the contradiction machinery in order to show this theorem. In general, direct proofs are much easier for a reader to follow than proofs by contradiction, and so if you determine that you can rewrite your proof as some variant on a direct proof, it's a good idea to do so. But let's take a look at another example of a proof by contradiction, and this is an example where rewriting it as a direct proof would be much harder to do, and it also illustrates that proof by contradiction is in fact more powerful than just what's demonstrated by proof template 12. Here I want to prove that the square root of 2 is not a rational number, and we'll prove this by contradiction. However, this theorem doesn't directly involve an if-then statement. We could make one up if we wanted to, but that would actually make the statement of the theorem less clear. And so it's worth noting that the idea of proof by contradiction actually applies more generally than just for proving if-then statements. In particular, we can strike out parts of our proof template, and we could, if we want to prove B, then we could suppose not B and show that this results in a contradiction. I will call this proof template 12a. And this is how we will prove that the square root of 2 is irrational. We hypothesize the negation of the thing that we want to prove, and we hope to eventually arrive at a contradiction. But from here, we can proceed by our usual approach of unraveling definitions. In particular, if a number is rational, then it is the ratio of two integers. A rational number can be represented as a fraction where the numerator and denominator are both integers, and we need for the denominator to not be 0. And for every rational number, there is some most reduced form of that rational number where we have divided out any common factors of m and n. And so if we have chosen the m and n that represent our supposedly rational number in the most reduced possible way, then we know that m and n have no common factors, and in particular, they can't both be even, because if they were, they would both have a common factor of 2. So if we have our quotient m over n equal to the square root of 2, then we could square both sides. And then proceed to simplify. And so here we've shown that m squared must be an even number because it's equal to 2 times some integer. And by the theorem we just proved, if m squared is even, then m must be even. And once we know that m is even, we know that we have some other integer that we can multiply by 2 to get m. And now we can substitute that into our previous equation. And now if we simplify, we find that n squared is an even number, and again, by our previous theorem, n must also be even. But if n and m are both even, that contradicts our hypothesis that they were not both even based on m and n being the most reduced rational representation of the square root of 2. And so we've reached a contradiction from which we can conclude that our hypothesis must not hold, and the only thing that we hypothesized here was that the square root of 2 is a rational number, so it must be the case that the square root of 2 is irrational.